Black holes are wild. Yes, they are the most compact things we know of, so dense that even past a certain point, light cannot escape. Even though we can't see inside them, the environments around black holes are brimming with bizarre activity. There can be a corona of hot electrons that occasionally spits out scattered X-rays. There's a bright accretion disk of gas and dust whose light is so warped by gravity, you can see the near and far sides at the same time. And I can't even begin to wrap my head around this estimate. There can be jets 20 million light years across. That is 140 Milky Ways end to end. So if we can't see black holes themselves, we need other ways of understanding them, like these extreme surroundings. That's why NASA continues to create new instruments to decode the chaos. So is there anything common about a black hole environment? Let's break down what we know. How does that process happen? How we know it? Where do you start with this? What am I looking at here?
If you look closely, it's a big mess.
And why we need to keep the questions coming. This is Black Hole Environments Explained. Not all black holes are the same or even chaotic. So scientists currently categorize black holes into 4 types. There are the ones that we've theorized exist, like tiny primordial black holes, which formed shortly after the Big Bang, and intermediate mass black holes that are sort of missing in the sense that they should be there, but we haven't confirmed sighting. We've observed plenty of stellar mass black holes that are at least 8 times the mass of our sun and the leftovers of supernovae. The most dramatic by far are the supermassive black holes, which are hundreds of thousands to billions of times more massive than our sun. In fact, they can reach sizes so big, they can span our entire solar system. When they're at the centers of galaxies, these monster black holes can become active galactic nuclei, or AGN. They fling a lot of material, and they produce a lot of kinds of light. AGN are black holes at their wildest. Jenna Kan researches black holes and their signatures here at NASA Goddard. She agrees that AGN are the drama queens of space.
I would call them the divas instead, but when you have an AGN, they want you to notice them as much as possible. So they're singing at every single wavelength they can.
But if you're looking at a full galaxy, do you almost just assume that there's a black hole there?
When we have a massive galaxy, so something that is like 1 billion times the mass of our sun, we can pretty much safely assume there's going to be a black hole in there. When you get to the low mass galaxies, which are the ones that I like studying the most, we don't know what's going on in them. But when you have a low mass AGN, that light can be easily overshadowed by stars and everything there. So you really need some kind of unambiguous, stars can't mess around with this diagnostic.
Where do you start with this, right? You get a map of dots. And these dots mean what?
What we'll do is we'll take a spectra of our galaxy, and if we see highly ionized, high energy features, that's good evidence that there's going to be an AGN there.
Would you say that this is the best indicator of a black hole?
That is very contentious. There is no one best option, basically. Every single tool that we have right now is fallible in some way. It doesn't work in some environment.
Enough talking about this environment like it's all uniform. We need a lesson in AGN anatomy. An AGN can have several different structures. The brightest feature is the accretion disk. In this Event Horizon Telescope radio image, we see the accretion disk around a supermassive black hole called M87 star. This plane of gas and dust orbits the black hole and heats up through gravitational and frictional forces. It emits light all the way from radio to X-rays. Above and below the disk, an AGN can have a corona. This superheated plasma of loose electrons emits a lot of X-rays. It's way less dense than the accretion disk, but way hotter. For a long time, scientists wondered how the corona formed, how it was shaped, how it interacted with the rest of the environment. So a recent study with NASA's IXPE telescope shows that the observed coronas likely extend in a plane like the accretion disk and possibly are a lot larger than we previously thought. One of the best methods to learning more about these systems is through analyzing something we call coronal lines. Now, Jenna uses spectroscopy to investigate coronal lines in AGN spectra. Yes, they look like squiggly graphs, but they tell us what elements are present, and more importantly, what isn't present. So a lot of the elements are ionized and are missing their electrons.
So these are highly ionized emission lines. 6 electrons have been removed from that iron atom. It's very, very bright in the center, which makes sense. That's the nucleus, that's going to be the brightest there, and then it gets dimmer and dimmer as you go farther out. And they're pretty good evidence to there being an accreting black hole in there, because it takes a lot of energy to even produce the ions that produce this emission.
Despite AGN being some of the brightest objects in the universe, they can also sometimes hide behind a dusty torus. Now, a torus is a thick bagel-shaped structure that is so dense we can't see the AGN unless the bagel's hole is facing one of our telescopes, or you seek the energetic X-ray signals. Now, scientists using NASA's NuSTAR mission, another X-ray telescope, think that as many as 50% of black holes are obscured by a torus. These dusty cloaks can even impact a developing galaxy. A lot of that thick debris will make its way towards the black hole, and if too much of the dust falls towards it at once, it can cause the black hole to sort of cough or burp, and a bunch of material comes out. And a hiccup that is big enough can even slow the rate of star formation. All of that is nothing compared to the achievements of a jet. So remember M87? Here's another image of it taken by our Hubble telescope. See that? That bright line is a black hole throwing a huge jet of particles, moving at nearly the speed of light. It does make you wonder. If black holes gather everything that comes too close, how does it propel particle jets? Cecilia Chiarenti, an expert in math, physics, and the wonders of black holes, has some ideas how. So what is going on? Why are they ejecting a lot of things when it seems like what we know is that they suck things up?
If you look closely, it's a big mess. If you have never seen it before, you have to imagine that the black hole is in the center. The accretion disk is around it. Kind of think about, the rings of Saturn that are around the planet. You have this big accretion disk around the black hole. And the jet is coming out like that. So you can think of a garden hose, and it's spraying out there in the cosmic distances, right? Like really big. The matter in the jet has to be coming from somewhere. So it's coming from the disk. And the question is, how do the particles on the disk, how do they get accelerated, pulled out from the disk, and directed outwards on the jet? So that is the mechanism that people try to study, and we have some ideas of how that works. Because if the black hole is spinning, you can steal a little bit of that rotational energy of the black hole and give it to something else.
Cecilia went on to explain that these jets also form because of a black hole's magnetic fields.
With the magnetic fields, what happens is that they are stealing a little bit of the energy, the rotational energy from the black hole. This extra energy in the magnetic fields is what is accelerating the particles in the disk to form a jet. Then it's kind of like the particle accelerators on Earth, where we use magnetic fields for accelerating particles.
Well beyond the black hole, the jet, the ionized and the energized particles, the X-rays and such, the gases just continue to spread. Because of their very nature, we will never see beyond a black hole's event horizon. We are doomed to see only the light that surrounds them. But there's still so many questions we can answer with that light. And with each new telescope we build, whether it peers through our atmosphere from the ground or studies the cosmos from space, they give us more clues as to how and why black hole environments behave as they do.